Welcome back, ladies and gentlemen. In this video we are going to talk about a theorem which has enormous implication in the field of vector calculus and in other fields such as complex analysis. The theorem is called the Green's theorem in the plane. If you have taken a course on vector calculus, then I believe you have heard about two theorems, namely the divergence theorem and the Stokes theorem. Both theorems are pivotal in the realm of vector calculus. In this video, we're going to talk about a theorem which is a precursor to those two theorems. So let us now go through the statement of the theorem and try to understand the different terminologies and the inherent geometry that is stated in this theorem. So first it talks about a closed region. A closed region, and it doesn't say anything else, so we are assuming that we can take a region like this and it is bounded by a closed curve. Of course, this region in the plane is going to be bounded by a closed curve, and I'm assuming it's a smooth curve, and it tells us that two functions are defined on the plane. One is m of xy, so it's the function of both x and y, and then n of xy, that's also the function of x and y, and these functions are continuous. Not only they are continuous, but you can differentiate them, and those derivatives are also going to be continuous. So m and n are continuous functions with continuous derivatives in R, right? So it might be everywhere else, but definitely it is the case in R. And then, if this is true, that we can write the theorem to be this statement here, which talks about, on the left hand side, the closed loop integral on the curve C, which is basically the boundary of R. And so on the right hand side we have an area integral, where of course the area is considered to be the R. This particular combination, where we have m dx plus n dy, is inside the closed loop integral. This is a line integral, and the right hand side, the partial derivative of n with respect to x and the partial derivative of m with respect to y, this pattern is directly linked to the pattern written in here. So here m is accompanied by dx. On the right hand side, m is differentiated by y. On the left hand side, n is accompanied by dy, and on the right hand side, n is differentiated by x. It's a nice little contrast, and on the left hand side we have a plus sign in between, whereas on the right hand side we have a negative sign in between. And of course, when we are talking about a curve, we'll have to mention the direction of the curve, or in the direction in which the curve traverses, and in this case it is the usual positive direction, which is the counterclockwise direction. So this is our C and this is our R, which is enclosed by this closed curve C, and within this region and on this region this statement is valid, which is known as the Green's theorem on the plane. So at this stage, this is what I'm going to do. I'm going to use this theorem, especially this statement of the theorem, and then I'll try to write down this theorem in the vector notation in two different ways that will generalize this theorem to the theorems of vector calculus, namely that of the Stokes theorem and the divergence theorem. So let's get started with. The first thing is to recognize that this object here, mdx and ndy, it looks a bit like a dot product, right? So for example, if we take r to be our position vector, and then this is given by, let's say, x I hat plus y j hat, where I hat and j hat are unit vectors in the direction of x and y respectively. And if we take the differential of r vector, we end up with dx I hat plus dy j hat, precisely because I hat and j hat are constant vectors, and so under this operation they do not change. So in that case, the left hand side, or at least what we have inside the parenthesis, which is m dx plus n dy, it can be written as mi, so that's a vector that we are constructing, plus n j hat. This should be dotted with dx I hat plus dy j hat. This is what we should get. And if I want to call this vector to be the a vector, then finally we can write it as a dot dr. Alright? So in that case, we notice if we take the cross product of the a vector in 3 dimension, what do we get? Well, we have a formula, right? We have the determinant, and in the top row we write I hat, j hat, and k hat. In the second row we write the partial derivative operators with respect to x, y, and z. And the final one, of course, we write m, n, and o. And this leads us to a vector which looks something like this: the partial derivative of n with respect to z times I hat plus the partial derivative of m with respect to z times j hat. And then of course inside a parenthesis we have the partial derivative of n with respect to x minus the partial derivative of m with respect to y times k hat. I highly encourage you to verify this by your own calculation. But notice what we have got here. Inside the parenthesis we have the right hand side, or at least what is inside the parenthesis in the right hand side of this equation here, and that is the coefficient of the unit vector k hat. So if I multiply or take the dot product of k hat with both left hand side and right hand side, I should only be left with this coefficient here, which is the coefficient of k hat. So by doing that we write, well, curl of a dotted with k hat. This is the thing we're looking for, right? So this gives us the quantity inside the parenthesis, which is the partial derivative of n with respect to x minus the partial derivative of m with respect to y. And so therefore the Green's theorem in the plane can be written as, so Green's theorem in the plane can be written as the line integral or closed loop integral of a vector field A over a closed curve equals the double integral over the area of the region R, which has been enclosed by the curve C. and inside we write as an integral the curl of A dotted with k hat. And we do notice if we generalize this to 3-dimension, this leads us quite naturally to the famous Stokes theorem. Okay? So that's why at the beginning I said the Green's theorem on a plane is actually a precursor to the Stokes theorem. Well, we can try to do the same thing but by a different method. And the same thing is to generalize the Green's theorem in a plane to 3-dimension. So one of the form gives us the Stokes theorem. Can you guess what the other form will give us? That's right, the famous divergence theorem. So let's go and check it out. Here we have a little figure drawn on the left top corner in order to signify what we are going to analyze geometrically. So of course, once again, like before, m dx plus n dy, the integrand on the left hand side can be written as the dot product of a vector with the displacement vector or the separation vector. And what we can do is in fact take the parameter of the curve C and write down the tangent vector in terms of that. So what we're going to do, we're going to write dr divided by ds, which is the arc length. So s is the arc length. It can be actually anything else. It can be any affine parameter, or it can be just any parameter, right? I don't have to specify what this is. And then we have A dotted with t, and we have ds, where t is the tangent vector. So this is the tangent vector, and s here should be any parameter of C, but preferably the arc length. Okay, because that's an ideal parameterization which we can rally behind. So then look at this figure. T is the tangent, right? Now if n, which has been drawn here, if this is the perpendicular to t and lying on the same plane as the r or c or the xy plane, in that case we'll notice that t is found if we take the cross product of k hat and n. Once again, n is the outward unit normal vector. So this is a unit normal vector. Okay, and it is normal to the curve because it is normal to the tangent to the curve at that point. Alright, so this would give us m dx plus n dy equals a vector dot t ds. But of course t can be substituted by k cross n, which you've just noticed. So k cross n ds. But then of course we can now see this to be a volume-like quantity, and in that case we know we can shuffle the quantities involved in writing down the volume. So instead of writing this, it is equivalent of writing a cross k and then taking the dot product with n hat. So if we say, alright, m I hat plus n j hat. So let me write it down. mi hat plus n j hat equals a, right? And of course we're going to say what b is. So b is another vector which we define to be a cross k. As it turns out, this results in n I hat minus m j hat. Okay, and if that is the case, we can take the divergence of b, and interestingly enough, we end up with the partial derivative of n with respect to x minus the partial derivative of m with respect to y. So this whole process, because we have a b here, and on the left hand side we have successfully replaced b, on the right hand side we notice the quantity in the parenthesis resembles the divergence of the vector b. So that gives us, or at least in the plane, b dot n hat ds. Okay, so this is somehow been turned into a closed loop integral, and then it should be r integrated over r, but integrated over what? It's actually the divergence of b dr. And notice you can generalize this, right? If you generalize this, you're going to find the divergence theorem in 3 dimension. So this is a very interesting result. This justifies why we should pursue the idea of Green's theorem in a plane, and you should also check out our video on the proof of Green's theorem. Until then, I have to say goodbye for now, and thank you very much for staying.